It's difficult to convey the true size of Nvidia's Blackwell GB202 chip without a proper point of reference. I can tell you that it has 92 billion transistors and a die size of over 750 square millimeters. These are just abstract numbers. But when we add a Zen 5 CCD for comparison, the perspective suddenly changes. GB202 is not just a large chip. That would be an understatement. GB202 is so massive, it reaches a die size we usually only see in server-grade AI accelerators. The chip measures 24.1 by 31.6 millimeters, which equates to a die size of 761.56 square millimeters, the largest GeForce chip ever. Let's go on a chip deep dive into the silicon heart of Nvidia's GB202 and try to understand what kind of monster Nvidia has created. Big shout out to Asus Tony who provided the chip. I've linked his video in the description below. The die shot was created by someone whose name I can't pronounce. I put it on the screen. And Kernel provided a high-res version of the image. Go check them out. I always like to start my analysis at the borders of a chip. That's where we usually find the I/O and memory interconnects. And it's no different with Blackwell. The massive 512-bit memory interface is hard to miss. The physical layer, which enables the interconnects to the GDDR7 VRAM, basically takes up the entire left, right, and top side of the chip. Left and right we can locate 6 32-bit PHYs each, and another 4 are on the top edge of the chip, for a total of 16 32-bit clusters. And since 16 times 32 equals 512, we can confirm Nvidia's claim. GB202 indeed has a 512-bit memory interface. On the remaining edges at the bottom of the chip, we can find the PCI-Express 5.0 SerDes with a total of 16 lanes, and a bit to the right, the display outputs. There are a few other clusters located in this area, some of which could be used for testing purposes, but it's hard to tell. The important takeaway is that the entire shoreline of the chip is called for. Nvidia's decision to go for a 512-bit memory interface basically predetermined the size of the entire chip, because it dictates how much shoreline is required. The chip can't be much smaller, even if Nvidia would have used less CUDA cores or less cache. That would just result in empty space in the center of the die. Once Nvidia decided on 512-bit, the die size was set in stone. If we zoom out a bit onto the PCB level, we can trace each 32-bit memory PHY to an individual GDDR7 memory chip. Because we are looking at a so-called flip chip, the chip sits face down on the PCB, which means left and right are switched in reality. The 4 top 32-bit PHYs are located right below 4 corresponding memory chips. For the PHYs on the left and right side of the chip, one memory chip is moved slightly lower, but because of the distance between die and memory, that's still an easy trace over the PCB. The PCI-Express lanes and display outputs are connected via the backside of the PCB, at least on Nvidia's Founder Edition models. Zooming in again, we can roughly make out 3 distinct areas. There's a top part and a similar mirrored area on the bottom, which is divided by a block in the center of the die. That block is the L2 cache. There's a total of 128 megabyte L2 cache on GB202, divided into 2 blocks of 64 megabytes. Let's break them down further. The smallest unit is a 2 megabyte block, and each cache row has 8 of these 2 megabyte blocks, resulting in 60 megabytes per row. 2 rows equal 32 megabytes and 4 of them 64 megabytes. The cache blocks are separated by what most likely contains a crossbar, so top and bottom of the GPU can talk to each other, and this area should also contain the command front end. To the left and right of the L2 cache, we can find the memory controllers. There are 4 on each side for a total of 8. Each controller can handle 64 bits, which corresponds with the 512-bit interface. The memory controllers are located right next to the L2 cache because the cache plays a big part in buffering the memory access. Back with RDNA 2, AMD introduced the Infinity cache, which was a large last-level cache in order to support the smaller 256-bit interface. With Ada Lovelace, Nvidia started to use a similar concept. But instead of adding a new cache level, Nvidia just increased the amount of L2 cache. With GB202, Nvidia's L2 cache has reached the same size as the original Infinity cache on Navi 21, which also had 128 megabytes. There's a narrow pathway that continues up and down from the crossbar in the middle of the L2 cache. This area is mostly used for Nvidia's D and encode units. There are 4 visible NVDEC code blocks in the top part, and below that I can make out a few NVENC code clusters. There are likely more of them I can't probably make out. kernel was able to label some more in his analysis. These areas are special fixed function units that accelerate, just as the name implies, video DNN encoding. It's how the GPU can run multiple 4K streams at the same time or encode a video while you're gaming and streaming, almost without affecting performance, because there's special hardware. The downside is that when you are not DO encoding videos, this area goes unused. GB202 also adds something new, a so-called AI management processor, or AMP for short. If we ignore the AI buzzword, it's a pretty cool new feature. The AMP is a tiny RISC-V processor that can offload some of the scheduling workload from the CPU and handle it right on the GPU. If you heard about Windows hardware accelerated GPU scheduling, or HACS for short, that's exactly what it is. But I can't locate the RISC-V processor on this die shot, at least not without help from an Nvidia engineer. Next, let's get to the most interesting part of the GPU, the CUDA cores and raster engines. In order to unravel the die shots in detail, it's always a good idea to look at the GPU block diagram first. And wow, does it look confusing. The weirdest part is that the actual die is much taller than it is wide, while the block diagram is literally opposite. I'm not sure that's the best way to draw the diagram, but that's what Nvidia provided. The important part is that GB202 is broken down into 3 main levels. It has 12 graphics processing clusters, GPCs for short, each of which contains 8 texture processing clusters, TPCs for short, and finally each TPC has 2 streaming multiprocessors, SMs for short. If that's still a bit confusing, don't worry, we will catch them all. Locating the 12 GPCs isn't hard. We just have to look for large repeating patterns. At this high level, the GPCs are divided into 4 areas, with each area containing 3 GPCs. Now that we have located the GPCs, let's zoom in and try to see if we can find the 8 TPCs that are supposed to be in one GPC. All I've done here is get really close and trace the smaller repeating patterns inside a GPC. Starting at the top, we indeed have 8 TPCs in each GPC. You can recognize a TPC by the 2 mirrored clusters left and right. These clusters are the SMs. And since the block diagram told us that each TPC has 2 SMs, that's another bingo. One interesting aspect I found is that from a physical design point of view, it looks more like there are 4 TPCs with 4 SMs each, instead of 8 TPCs with 2 SMs. One TPC always has a slightly different layout, but if you combine it with the next one, it creates a nice even square. But it doesn't matter if it's 4 dual TPCs or 8 single TPCs, the result is the same. Because of the resolution of the die shot, the SM level is the furthest we can go. There's no resolution left to zoom in more, but the block diagram does go further. Each SM contains 4 clusters of CUDA cores and a single ray tracing core. The CUDA core clusters are grids of 32 ALUs that can perform either a 32-bit floating point or integer operation. This is an architectural change. On Ada Lovelace, the 32 ALUs are split in 16 ALUs that could only do floating point and 16 that could do both integer and floating point. With Blackwell, all CUDA cores are now capable of integer and floating point. Each grid also contains 1 tensor core for matrix multiplication and 1 texture unit or TMU. I think it's funny that the TPCs are still named after the texture units, even though the CUDA cores are the real focus here. To recap, GB202 has 12 GPCs with 8 TPCs each for a total of 96 texture processing units. Each TPC has 2 SMs, which means there are 192 streaming multiprocessors. And each SM has 1 ray tracing core, 4 TMUs, 4 tensor cores, and 128 ALUs or CUDA cores. If we add it all up, there are 192 RT cores, 768 TMUs, 768 tensor cores, and 24,576 CUDA cores. That's a lot of cores. But wait, there's one more thing. Each GPC also contains 1 raster engine. That's where the raster operations or ROPs are located. The raster engine is located at the end of each GPC. Since there are 12 GPCs, there are also 12 raster engines, and each raster engine contains 16 ROPs. That's a total of 192 ROPs for the full GB202. With almost all areas of the GB202 die labeled, let's take a step back and look at the whole chip. The 512-bit memory interface takes up about 108 square millimeters, or over 14% of the die area. If we add the 15.5 square millimeters for the memory controllers, that's over 16% of the chip dedicated to the memory system alone. The L2 cache is no slouch either. It uses around 104 square millimeters, which is also close to 14% of the die and very similar in size to the memory physical layer. With 337 square millimeters and over 44% of the entire chip, the compute parts of the GPCs takes up by far the most amount of space. Compared to that, the rest of the engines seem almost small with only about 54 square millimeters or 7% of the die. And the PCI-Express 5.0 interface is actually tiny at around 6 square millimeters and less than 0.8% of the chip area. Just like its predecessor, the RTX 5090 does not use a fully enabled GB202. Let's see which parts of the chips are disabled in a 5090 and which are untouched. The memory system is untouched. The 5090 uses the full 512-bit interface and all memory controllers are active. But that's not true when it comes to layer 2 cache. The 5090 does not have access to the full 128 megabytes. It's cut down to 96 megabytes. That means 25% of the cache is disabled. It's still the same bus width to a 2 cache ratio as on the 4090, which combined 384 bits with 72 megabytes. Nvidia also cut down some of the D and encode blocks. The 5090 has 2 active D and 3 active encoders. Out of the 192 SMs on GB202, 170 are active on the RTX 5090, which is a reduction by 11.5%. It's a bit more than one whole GPC. To be precise, Nvidia disabled 11 TPCs. I think it's a combination of one whole GPC and 3 TPCs and another GPC, like I've visualized here. The one fully disabled GPC also disables the corresponding raster engine. That's why the 5090 has 11 of them for a total of 176 ROPs, which is the same amount as on the 4090. And because the 4090 has slightly higher clock speeds, it actually has a slightly higher pixel fill rate than the 5090, which I found funny. But before you scream, GB202 is pure AI GPU, which I would somewhat agree with. A quick reminder that AD102 and the RTX 4090 has very similar proportions. In many ways, GB202 is a beefed up AD102. The disabled areas on GB202 amount to roughly 80 square millimeters, which is about 10.6% of the entire die. Of course, the areas I've marked here can be different from the areas that are actually disabled on each chip. With a die that large, there's a high chance of defects being present inside the chip. Nvidia is disabling these areas to increase the numbers of working chips they can produce. And if we look at the expected yield of GB202, you can see why Nvidia is doing that. Companies are usually very secretive when it comes to exact yield numbers, but we can come pretty close. Using the semi-analysis die yield calculator, all we have to do is put in the chip measurements. I've set the scribe lines to 0 because the measurements I use for the die size already includes them. And I've also lowered the defect rate for the TSMC 4N process node to only 0.08, which is a really good value. With these inputs, the yield calculator gives us a yield of only 56%, which means a single 300mm wafer only has 39 good dies. If we estimate a conservative $15,000 per wafer, that's about $385 per chip. In reality, Nvidia will be able to use more than that because, as we just learned, the RTX 5090 does not use a fully enabled GB202. By disabling parts of the chip, Nvidia can salvage more chips. But even if that gets a number of good dies to, let's say, 50, that's still $300 per chip, just in pure wafer costs. I estimate the cost of a GB202 for an RTX 5090 to be somewhere between $300 and $400. From what I've heard, the 4N process node Nvidia is using isn't actually TSMC's N4 node, but most likely N5P with a new name. It's the exact same process node as used for Ada Lovelace. Gaming Blackwell did not get the process node upgrade to 4NP. But the chip isn't everything. 32GB of GDDR7 memory most likely adds another similar amount of cost on top. If we estimate $350 for the chip and another $350 for the memory, we are already at $700. Then we have to add the costs of the multi-layer high-density PCB, the absurd VRM setup, the packaging, the over-engineered cooler, and so on. And that's still all without any R&D costs, transport or taxes. There might not be nearly as much margin on such a card as you would expect. And the hardware stores also want to make some money. From my point of view, it's very obvious that GB202 has more than just a gaming focus. The best indication for that is the super wide 512-bit memory interface. The RTX 4090 combined a 384-bit wide interface with 21GB per second GDDR6X memory, resulting in 1008GB per second memory bandwidth. Blackwell makes the jump to next-gen GDDR7 memory. Nvidia is using chips that can run at up to 32GB per second, a 52% increase over the 21GB per second 4090 memory. With the same 384-bit interface, but using the fastest G7 modules, the 5090 would have achieved a whopping 1,536 gigabytes of bandwidth. Clearly more than enough to make sure the 33% additional CUDA cores are not bandwidth starved. Sticking to a 384-bit bus would also have meant the same L2 cache size as on the 4090, another way to save die space. And it's not only about silicon area. A large memory interface also consumes a lot of energy. The 512-bit bus plays a major part in the 575-watt TDP. I'm interested to see how much power you can save by underclocking the memory on the 5090. Running the GDDR7 modules at 24 GB per second would still result in about 1.5 terabytes per second of bandwidth. Combining a wide bus with fast memory indicates a clear AI focus. GB202 will also be used for the RTX 7000 workstation AI accelerators, and there you can never have enough memory and bandwidth. The 512-bit interface also allows for 64GB cards using clamshell memory and up to 96GB when using the new 3GB GDDR7 modules. These chips will then most likely also run at memory speeds of 32GB per second for over 2 terabytes of bandwidth. The same AI focus can be seen in the changes to the CUDA cores. With Blackwell, all cores are now able to run either integer or floating point operations, while before half of the cores could only handle floating point. This change vastly increases the integer performance, from 41.3 TOPS on a 4090 to 104.8 TOPS on the 5090. Combined with support for new Int4 math, GB202 offers a 4x increase in AI TOPS. If Nvidia would have designed GB202 with a pure gaming focus in mind, they would have most likely kept the 384-bit interface. 24GB of VRAM are still more than enough, and they also cost less. The smaller die would have been cheaper, and the power budget could have been used to clock the CUDA cores higher instead of powering the super wide memory interface. Such a card would not only consume less energy, but also be cheaper to produce. There's no doubt, GB202 is a monster of a chip. Its sheer die size is testament to that. And while many of Nvidia's design decisions were clearly AI focused, it doesn't really take away from the performance of the chip. Yes, a smaller and less power-hungry chip with a similar gaming performance would have been possible, but there's also something attractive about a chip that goes all out. I still remember Nvidia's 8K gaming stunt with the release of the RTX 3090. But if you aren't playing Cyberpunk or Alan Wake 2, the 5090 might actually be a pretty capable 8K card. There's certainly enough memory bandwidth and VRAM available. GB202 also shows how difficult it is to provide a meaningful performance uplift on the same process node. It's not impossible, Zen 3 used the same node as Zen 2, but it's increasingly hard to achieve. The physical EUV reticle limit is 858 square millimeters. You can't make a monolithic chip larger than that. At over 750 square millimeters, GB202 is getting very close to the maximum. If Nvidia aims to deliver a tangible performance uplift in the future, a potential RTX 6090 either has to use a much improved process node, for example N3P, or better yet N2, or Nvidia has to start using a chiplet architecture, like they introduced with GB200. I hope you found this video interesting, and see you in the next one.